So similarity measures for time series. We'll start with simple similarity measures, the Minkowski measure actually, and the uniform time warping. So Minkowski distance is very easy. We model each time series as an n-dimensional vector, or just think that a time series just models an n-dimensional vector, time series of length n, and then given two time series with the same length, we can just use the LP norm between the two n-dimensional Euclidean vectors, like we know how to do that, of course. Yeah. So properties, each time slot in X is compared to each time slot in Y, obviously. Yeah. So if we have some variations along the time axis, Minkowski is obviously extremely sensitive. Yeah. And also in the baseline thing here, it's limited to time series having the same baseline, scale, and length of obviously. Yeah. But if you work with time series that have those properties, and you want to have a time by time slot comparison, no variation along the time axis, then Minkowski can be a good idea. So yeah, and well, if the two time series X and Y do not have the same length, they could still be considered to, or still can be measured, can be considered similar. For example, if they have different baselines or amplitude scales. So if we want to be invariant against some of those effects, we can normalize them by using the preprocessing stuff from above. For example, shifting by the average value, which we got to know as offset translation in the previous podcast. We can scale it by the standard deviation, which is amplitude scaling. So this is all easy to do. The only thing is, so shifting and scaling is performed on the amplitude axis, so on the y-axis actually. Yeah. Still, if we have time series of different length, that does not help. Yeah. So what can we do if we have time series of different length? Can we also do some scaling along the time axis? And of course we can do that. So for comparing time series of different length, for example with Euclidean or LP norm, yeah, Minkowski distance, we need to scale the time series or both time series along the time axis to get to so that they have the same length. Yeah, and we can do, for example, two different things. We can do so-called upscaling, which increases the resolution. So for each value, we repeat the value omega times, yeah, so that the whole thing is obviously the correct length. Yeah. And downsampling is the reverse thing, obviously. So we decrease the resolution. So only multipliers of omega are used here in that case. And yeah, we just set each new each new value here to typically to the mean value, or to just erase the time slots from the original time series. Yeah, just erase them. So each omega time slot will be removed, or will be kept. All the other time slots from the original time series will be removed, and then we obviously have decreased the resolution by just downsampling the time series. Of course, be aware of downsampling. So upsampling, of course, can also introduce a lot of bias and artifacts, but downsampling, here you really lose those time slots here. As you see it here, you just keep this one here, this one here, this one here, this one here, or this one here, whatever. Yeah, so you only keep here each jeden zweiten time slot. Sorry, I have a hanger. Okay, Good. So, and that is actually used in uniform time warping. So the idea is to scale both time series along the time axis to the same length and then just utilize Euclidean distance. So it's very easy. You can also, of course, use any other Minkowski metric here. So yeah, it's just a little bit ridiculous that you use an extra term like uniform time warping for applying two specific things that people know for a long time. But anyway, so given two time series with different length now, the squared uniform time warping distance is, yeah, you just upsample both to, so x has a length n, y has a length m, so you upsample them to the length of m times n. So you have to upsample x by m and upsample y by n, and then you apply squared Euclidean distance in that case. Yeah, and if you take the square root, then you have obviously the non-squared uniform time warping distance. You can also, instead of upsampling both x and y with m and n, yeah, for the upsampling you can just use the lowest common multiple, of course, which is sometimes a better idea because, as I said before, upsampling, downsampling you lose information, upsampling you introduce information that artificial information, so you may introduce some bias. So always be a little bit careful about up and down sampling, specifically downsampling, but also upsampling.